In linear regression, we normally think of this picture here. We have some data, these blue points, and we want to find the line that best fits this data. And how do we define that best fit? Well, we define it in terms of square residuals, minimizing those square residuals. But if this was linear regression, then we wouldn't be able to do very much with it because very few relationships we're interested in are linear like this. So is this really what we mean by linear regression? Actually, no, not in machine learning. This is not what we call linear regression. This is an example of it. In linear regression, we can in fact model highly nonlinear relationships. So what do we mean by linear? Well, that's what we're going to find out. Let's suppose that our data looks like this. Well, we can't fit any straight line through this. It would be completely useless. Whatever straight line we find, it would not be a very good fit. What we really need is a function like this, a quadratic. This does appear to be a quadratic or approximating quadratic. So what does this function look like? It contains some coefficients, theta naught, theta 1, theta 2, and the x term here and the x squared term here, and this we call a bias. Now here's the key thing to realize. This is still linear regression. So what do we mean by linear regression? We mean linear in the parameters, and that means usually not in the input. It can be linear in the input, but usually it's not. So the key thing here is that our function that we're proposing is linear in each of these thetas. It's not linear in x because we have an x squared term here. As long as we have linear thetas, there's no log or exponential or sine or squared or cubed, it's linear regression. So just to give you a counterexample, we can look at this function here. Now this is obviously nonlinear in x because it contains an x squared, but it's also now not linear in the thetas. It's linear in this theta, theta 2, but it's not linear in theta 1. We've got log of that. And it's not linear in theta naught. We've got the cube of theta naught. So this is an example of a nonlinear regression. Now, let's suppose we do actually have a linear in x model. And suppose that we have the input x, which is a vector with coordinates or coefficients x1 to xp. We can also call these covariates. We could propose this model, which is linear in x and theta. So here we've got a model that is linear in both x and theta. What does least squares linear regression do? Well, it minimizes the difference between this prediction at a particular value of x and the values that we measured, right, the yi's. And then it squares that difference, sums that all of these squared differences together over all of the data points and minimizes it. So let's write down the predictions over the whole of the data set. So the pair x1, y1 to xn, yn. Well, y1 is approximately this function at x1, the function I just wrote down. That's equal to theta naught plus theta 1 times x11. That's the first coefficient of x1. Theta 2 times x12. That's the second coefficient of x1. Down to plus theta p times x1p, which is the pth coefficient of x1. And similarly, for x2, we have y2 is approximately f theta of x2, which is theta naught plus theta 1 times this plus theta 2 times this, etc., down to the nth data point. Now, this matrix here we call a design matrix, and I will give it the symbol x, and theta is the vector of these coefficients, and y is the vector of our targets in our data set. So the least squares problem can be posed like this. The best theta, let's call it theta hat, is given by minimizing the total square error. So the differences between each of these yi's and f theta xi's squared and then summed over all of the data points. Now we can write this sum of square errors as this vector minus x times theta, design matrix times theta, dot product with itself. So how do we solve this problem? Well, we need to find the gradient of this, which is the total square error, which is equivalently the gradient of the 2 norm of this vector, which is the square error. And once we found that gradient, we set it equal to 0 and we solve the equation. So let's set r theta equal y minus x theta. Then what we're looking for is the gradient of r theta squared, the gradient of y minus x theta squared, which is given by this formula, twice the gradient of r theta transpose times r theta. So what is r theta? Well, that's just this. What's the gradient of r theta? Well, it's the gradient of this with respect to theta, right? And that's just minus x. And then we have to transpose it. So we get minus 2x transpose times this. And this gives us the normal equations. So this has to equal 0. So x transpose y minus x theta is 0, or we get this equation, x transpose x theta is x transpose y. Now we multiply both sides by the inverse of x transpose x. And you can see what will happen here. If we multiply this side by x transpose x inverse, so we multiply it on the left, that will cancel with that. And here we multiply it on the left, x transpose x to the minus 1, and that will give us our solution. Theta is this inverse x transpose y. So that's what we get as the solution, our theta hat. And we call this quantity the Moore-Penrose pseudo-inverse. So this gives us solution vector y is approximately x times theta hat. Now, among all solutions of the form x theta for some vector theta, this gives the smallest square error. Now, how do we handle nonlinearity in x? So that's linear in x and theta. Now, in our linear in x model, we have what we can call features. These are the coefficients of x, and each of these features is trivially a function of x. So this is our model, and each of these we are calling features, and they are trivially functions of x. So x1, for example, we can consider as some function, let me call it phi1 of x, where x is x1 all the way up to xp. And what is this function? Well, it simply selects the first coefficient. And similarly, we can define x2 as some function phi2 of x, or we define phi2 of x as the function which simply selects the second coordinate down to a function phi p of x, which simply selects the pth coordinate. Okay, so here is the key insight. What if we replace these features with just some general functions? Let me call them phi1 to phi m of x. And we choose how many of them we want. We don't have to have p. We can have any number. So instead of this model here, why not this model, which is a sum, a linear combination of some functions of x with this bias term theta 0. Now, the key thing to note here is that this is still linear in the parameters. It doesn't matter what these functions are, whether they are linear or non-linear. It's still linear in the parameters. Now, essentially what we've done, and I'll come back to this in the last slide, is transform our input, which was this, into a new input, which is a vector of these functions. Let me call that phi of x. And phi of x is actually a feature map. It takes an input x and gives us a feature vector phi of x with m components. It lies in Rm. So let's have a look at a classical example. So we'll take the example of x being a scalar, and we will use monomials. So for phi1, we're going to use x. For phi2, we're going to use x squared. Up to phi m, we're going to use x to the power of m. So we have this model. f theta of x is equal to a polynomial. And this is surely not linear in x, but it's still linear in each of the parameters. So let's write down what our approximations would look like in each case, so for each data point. So f theta at x1 is theta naught plus theta 1 times this plus theta 2 times this up to plus theta m times this, the last function evaluated at x1, and similarly f theta at x2 and f theta at xn. So we can write this matrix system here of our approximations. And this matrix we still call a design matrix, but now I'm going to give it a symbol phi rather than x. Everything else remains the same. In the monomial example with the scalar, we have this matrix here. So f theta at x1 is theta naught plus theta 1 times x1 plus theta 2 times x1 squared up to plus theta m times x1 to the power of m. And similarly for the other predictions. This matrix has a special name. We call it the van der Monde matrix. So what is the least squares problem now? Well, the only thing that has changed is we have swapped x for phi. We still want to solve this problem. We want to find the square residuals between our data point yi and the prediction f theta at xi using this new model with these new functions, summed over all data points, which is still y minus design matrix theta transport dot product with itself. And the solution is exactly as before, but all we do is replace x with phi. So we get the solution of exactly the same form as before with now phi in place of x. And this is still called the Moore-Penrose pseudo-inverse. Now we can think of these features, phi I of x, as new inputs. So let me define zi as phi I evaluated at some x. Then we can form the vector z, which is the vector of each of these for each of these functions, basis functions. So z1 to zm. And this is essentially our new input. So we can have or can interpret our model with general basis functions as a linear in Z model. So what we're equivalently doing is posing this model. F theta of Z, now not of X, but of Z, is equal to this function here, which is linear in the thetas and linear in Z, linear in each of its components or coordinates. So for example, what we could do, once we've specified phi 1 of X down to phi m of x, for each of our x's in our dataset x1 to xm, let's pick the jth one, we could find x1j down to xmj. And this would be z1, the first coordinate, sorry, j, the first coordinate, down to z, j, the mth coordinate. So we would have a vector here, z, let me call it j, zj equal to z1j down to zm of j. And this simply replaces xj. So we replace xj with this. And we do that for all of the x's. And now we have a data set y, j, zj. And we just work with that and pose this model here. So what are we doing? Well, essentially what we are doing is classical linear regression in feature space, because this z is a feature vector and it lies in some feature space. And the solution vector we will get also lies in feature space. So that takes us to the end of this. So hopefully that makes it clearer now what linear regression actually means, at least in machine learning, not the very narrow definition that's used in some areas of statistics.